Hello everyone and welcome back to another chemistry video. As you are aware, we have been studying electrons, and who knew that there is so much to learn about electrons. They're very important, especially for chemical reactions and other properties of atoms. But what's kind of cool about electrons is they have what you could call an address. They have these quantum numbers that allows us to kind of predict where these electrons are in space. But electrons, as we know, are always moving and are super tiny, so we can't know for sure. So a scientist named Heisenberg came up with the Heisenberg uncertainty principle. If I remember how to spell principle. Okay, there's an I there maybe. I don't know. Okay, so what Heisenberg's uncertainty principle is that there's always some uncertainty. I know, it's so surprising, right? Always some uncertainty about the exact position and momentum of an electron, because they're super tiny, they're always moving. It's hard to kind of check those things down. But using probability in quantum mechanics, we can describe the electron's position with best amount of accuracy that we have. So, as we learned in our flame test lab, which was super cool, electrons have ground states and excited states. So when an electron is in its ground state, that's when it's most stable and at its lowest energy. And this is when the electron, and lowest energy the electron can have within three dimensions of an atom. So it's kind of when it's just chilling there, hanging out. So when an electron's at its ground state, we use quantum numbers to say where it is. It's kind of like the electron's own personal address. And so these quantum numbers specify atomic, orbital locations of electrons. So we have another principle, which is Pauli's exclusion principle. Exclusion. Okay, so what Pauli's exclusion principle says is that no two electrons within the same atom can have the exact same four quantum numbers. It's just like house addresses. No two people have the same address. So no two houses have the same address. So there are four quantum numbers. So let's start with the principal quantum numbers. So we have n, which is our principal quantum number. That should actually be a lowercase n, not an uppercase. Oops, that's not gonna work. Okay, so n is our first quantum number. It is our principal quantum number, and it designates major energy level. So this is the energy level where the electron is. And n ranges from 1 to 7, just like there's 7 periods on the periodic table. So as n increases, so does the size of the energy levels. Increases, so do the energy levels. Because as electrons get farther and farther away from the nucleus, the positive protons have less of an attraction on the negative electrons. So they're kind of farther out because, if you only have one electron, that's going to be really close. But if you have like 73, there's way more room for them to. They have to spread out, and so they're going to have larger energy levels. So, in an energy level, you can have a max of 2n squared electrons per energy level. And we will see this come into play with sublevels, which is our next quantum number. So our next quantum number is L, which you're probably going to want to write as a cursive L, so you don't confuse yourself with a 1. So this is our subsidiary quantum number. Okay, so the subsidiary quantum number. And so L specifies particular sublevel and shape of the orbital. So the value of L depends on N, and L can range from 0 to 3. And just remember that 0 doesn't mean nothing. It's just that's the number it's given. And so since L depends on N, really your L ranges from 0 to N minus 1. If you're in energy level, yes, I lost my train of thought there. So there are 4, since there are 4 L values, that means there are 4 different types of orbitals. So to start, we have L equals 0, which is also the S sublevel, which has a spherical shape. And so for these L values, there can be a max electron amount of, so this should go up here, but so for every L number, there's a max electron amount of 2 times 2L plus 1. Let's go up there. Okay, so for L equals 0, the max amount of electrons you can have is 2. And that's why there is 1 orbital, because orbitals can have a max of 1 pair of electrons. And orbitals are just the position in space an electron is in. So that is L equals 0 is S. So then you have L equals 1, and that's your P sublevel, and it has what books call a dumbbell shape, which doesn't really make a lot of sense. You've seen what these look like. I like to think of it as a peanut shape because it starts with P, and that's kind of what it looks like. It looks like an infinity too. Whatever is going to help you remember that L equals 1, P, peanut shape, and so for L equals 1, you can have a max of 6 electrons, since there are 3 orbitals. So then we have L equals 2, which is our D sublevel, which has a max of 10 electrons because it has 5 orbitals. And then our last one is L equals 3, which is our F sublevel. And that has a max of 14 electrons because it has 7 orbitals. So those are the subsidiary or sub-level quantum numbers. Our next quantum number is M sub L, and that is the magnetic quantum number. And so what the magnetic quantum number designates is it designates orientation of the specific orbital within the sublevel along x, y, and z axis. And orbitals, remember, can have a max of 2 electrons. So ML ranges from negative L to positive L as integers. So if you are in sublevel S, remember L equals 0, so M sub L would be 0. But if you have L equals 2, which is your D, you'll have negative 2, negative 1, 0, don't forget 0, 1, 2. So since there can be 2L plus 1 orbitals, so 2L plus 1 orbitals. So that's how many orbitals each sublevel can have. And then our very last quantum number is M sub S. And M sub S is the spin quantum number. And so what the spin quantum number does is it designates the direction the electron is spinning in. And so if you have one electron in an orbital by itself, you have one unpaired electron, its M sub S is going to equal positive 1/2. And then by convention, if you have a paired electrons, that second electron is going to be negative 1/2, or in that sum level, you're going to have MS equals plus or minus 1/2. And the positive one is clockwise, negative one is counterclockwise. So, yeah, so what can we do with these? Well, now we can name electrons and kind of tell where they're placed in spaces. So I'll do one quick example. We'll do nitrogen, because that has 7. So the electron configuration for nitrogen, which I am making a video on, it's 1s2, 2s2, 3p3. So remember, this is our energy level, and then this is how many electrons our sublevel can hold. So the best way to go about these is to make a chart. So we have what electron we're doing, our energy level, our sublevel, our magnetic, our orbital, and then our spin. So that's our little chart. So we're going to start with the first set of electrons. So we know in this S sublevel, we have 2 electrons from that exponent. So we're going to say electrons 1 and 2. And so from this coefficient, we know they're in energy level 1. S sublevel is L equals 0. M of L is negative to positive L, so that would just be 0 again. And then the spin, since we have both electrons paired, is going to be plus minus half. Those are the first two electrons. So the next electrons are going to be 3 and 4. They're going to be in the second energy level. Again, their L is 0 because we're in S, so is the M. And again, since they're paired, we have plus minus a half. And then for our P level, remember, due to Hund's principle, the electrons don't pair up automatically because that takes more energy. They're going to spread out. And so in this P, we have 3 electrons, but remember, if you do the orbital filling diagram, they would be like this. So we're going to have electrons 5 is going to be its own, electron 6, and electron 7. So those are going to be the final ones. So we know they're all in energy level 2, not 3. 2, 2, 2. P is L equals 1, so they all have an L of 1. So here is where M sub L is negative to positive L. So you're going to start with this first one, and you're going to go negative L, 0, and then positive L. And in the spin, since they're not paired up, they're just going to be positive 1/2, if you want to put the plus sign there. So that's how you would fill out one of these little charts. So say we didn't do nitrogen, say we did oxygen, which would be 2p4. We would come back in and put electron 8 here, and then all these would be same, but then we just have plus minus there. So that is not very quick, but that is the rundown on quantum numbers. This chart kind of goes over it all. N, energy level, L is your sublevel, M sub L is your orbital, and then MS is your spin. And yes, I hope that helped. Sorry, this one's kind of long, but yeah, good luck on everything coming up with chemistry, assessment-wise. So, thank you so much for watching. Bye.